Good afternoon and welcome to today's highly anticipated webinar. My name is Ashley Inman with Digital Niche Agency. I'm excited to be here with the team from Gravity Power. We're excited to kick off this webinar, but before we started, I wanted to go over a few things that we cannot discuss just due to compliance reasons. So we're unable to answer any questions regarding financials, projections, or use of funds on this webinar today. For those questions, please visit the Gravity Power campaign page on Start Engine, where you can use the discussions tab to get those questions answered. I'm going to drop the Start Engine raise page in the chat box below for everybody, so you guys all have easy access to that. All right, and then if you have any issues accessing that campaign page, please let me know. And then the last thing to note is that this is a Q&A webinar, so be sure to put your questions in the chat box below throughout the presentation. We will open it up at the very end to get those questions answered for you. So without further ado, I'd like to pass it over to the Gravity Power team, who will guide us through this exciting webinar for today.
Hello, let me introduce you to the team that will be presenting today. I'm Brad Payton. I was the first investor in Gravity Power, and I continue to invest today, including in this Start Engine offering. I'm a professor emeritus of mechanical engineering at the University of California. I hold numerous patents, and I've launched several startups over the years. Jim Fisk is our inventor and chief technologist. I'm proud of the great work that Jim and the Gravity Power team has done with this great groundbreaking technology. Educated at MIT, Jim is a serial entrepreneur, very experienced with R&D and commercialization programs. Steve Tabor has joined us recently as our chairman and CEO. Steve has led several startups, has been deeply involved with policy making for the energy sector in California. Steve was educated at Princeton and Berkeley. We want to walk you through the market opportunity today for energy storage, how the Gravity Power technology works, and why we believe that the Gravity Power value proposition is so compelling. Let's start with the market. Steve?
Thanks, Brad. Let me share some slides here, folks. Give me having some computer glitches. There we go. We all know that we need to take carbon out of our electricity supply in order to mitigate global warming. Energy storage is a necessary enabling technology to accomplish that, and I want to walk you through why. I'm going to show you some very simplified charts of how electricity is consumed and how it's generated during the day. Let's take a typical day. This is noon, this is midnight. These are the hours when most people are using electricity. That drives a consumption curve which looks something like this. Energy use is low during the night. In the morning, it starts to pick up when people start their day and they, start going about their tasks, cooking and the like. Loads typically increase as the day goes by, and usage increases, air conditioning loads increase, and then it reaches a peak in the early evening. Now, let's see how this consumption curve matches up with energy supply. This is a simplified version of a typical solar energy resource. It's too much energy during the middle of the day, not enough energy at other times. Now, of course, the solar resource is not constant like this because clouds pass over the sun, causing generation to drop off. That in turn creates instability in the grid, causes blackouts, especially in small isolated grids like Hawaii. This is the wind resource. It's a better fit for consumption than solar is, but there's still a lot of wind energy which is wasted late at night. And wind, just like solar, wind is not constant. It gusts and it lulls, and so all of that creates instability problems on the grid. Nuclear generation, also a carbon-free generation source, is a different sort of problem because nuclear energy, nuclear plants have to run flat out 24/7, constant all the time. They cannot ramp up and down. That results in not enough generation during the peak hours and too much generation at night. So what all of this amounts to is a mismatch between energy supply and energy generation, between energy demand and energy supply. And this is really what our job is and what our opportunity is to take all that excess energy that's going to waste and move it to the time of day when customers need it so that the energy consumption can match supply. It's basically taking all those squiggly lines and making those squiggly lines match the demand line and making generation match demand. This is a simplified version of what is known as the duck curve. There's some debate as to whether that's a duck or a seahorse or the Loch Ness Monster, but whatever it is, it's often called the duck curve. This is the duck curve for a typical day in California. And what it shows is the difficulty of managing the grid as renewable generation increases. And the greater the percentage of renewable generation you have, the worse the duck curve problem is. And basically, it amounts to a need to add 13,000, this is in California, a need to add 13,000 megawatts of generation in just 3 hours. And that has to happen every single day. And so that's a major grid management problem, which grid operators all over the world are facing. Now, how much generation? I'm sorry. This also shows why storage is critical, because that's exactly the kind of problem that our technology and other storage technologies are designed to address. So we know we need storage. We can see the size of the problem on the grid. The question is, how much storage does that amount to? Well, the rough ballpark answer is at least order of magnitude 10 times as much as we built already. Currently, there are 167 large storage projects in the world, some under construction, some already built. We need to add at least a couple of thousand more large projects. These are projects which cost $1 billion and up. We need to add at least a couple of thousand more of those in order to decarbonize the grid. McKinsey has done a lot of work on energy storage and the market for it, projects a demand of about $1 trillion between now and 2040. To date, almost all of the storage on the grid has been installed in the form of pumped storage hydroelectric. Pumped storage is quite a simple concept on energy storage. You have two reservoirs, you have one up high, you have one down low. To store energy, you pump water uphill from the lower reservoir to the upper. To generate energy, you let water flow downhill to generating energy. And that's basically how it works. This is the dominant form of storage on the grid, over a 90% market share. Utilities love pump storage because it's cost effective, it's reliable, it's highly round trip efficient, it stabilizes the grid. So there's a lot of advantages to pump storage, but there's one really big disadvantage, and that's that it is very damaging environmentally. As a result, whenever a pump storage project is proposed these days, and the utilities are proposing a lot of them, they really need to add storage. Whenever a pump storage project is proposed, it attracts a lot of opposition and almost invariably does not move forward. As one example of that, this is the Eckdorf pump storage project in Austria. This was first proposed, if I have my dates correct, in 1970, and it lingered for a long time because of opposition, never moved forward. In 2008, it was proposed again. The same project was proposed again. Again, it attracted a lot of opposition, and it's all because of environmental issues. This is the environmental impact statement for that project, and if there's that many boxes, you know there's a lot of impact. And this is typical of what happens with pump storage projects. This was first proposed over 50 years ago. It still hasn't moved forward. As one other example closer to home, again, I'm going to try to get my numbers right. In 2000, Jim, correct me if I'm wrong. In 2009, there were 43 major pump storage projects proposed in the United States, which were in the queue for interconnection to the grid. And as of today, none of them have moved forward. So the bottom line is we need a lot of storage, and there is no realistic way that we see for pump storage to make a meaningful dent in that. That has created a market vacuum that many companies, including Gravity Power, are looking to fill. The main competition for grid storage these days is lithium-ion batteries. Now, lithium is great. You know, I have it in my phone. You all have it in your phone and my laptop. And, you know, if you have an EV, it's in your EV. Lithium is great for that, but it really doesn't make sense for grid storage. Lithium is environmentally damaging both at the supply end, where you have the impact of mining, and the disposal end, where lithium is toxic waste. Has a short service life. Grid-connected lithium batteries typically last about 15 years. After 15 years, you have to throw it out and buy another one. Also, the supply of lithium is constrained. There's only so much lithium on the planet. And the burgeoning demand for lithium for mobile uses like phones and the like has driven the cost of raw lithium up about 10 times. So bottom line, it's much too expensive for grid storage, much too problematic. Then there's a bunch of other technologies out there like compressed air and redox is reduction oxidation. That's also known as a flow battery. And then there's mechanical lifting of weights up and down. You've probably seen a bunch of those around. Excuse me. And they all seem to have their own problems, either around low round trip efficiency or siting issues or environmental issues and cost. None of these technologies seem, to our way of thinking, to have the compelling value proposition of gravity power. Now, our customer value proposition, I should say it's our proposed customer value proposition because we haven't built any yet, but it's really pretty straightforward and pretty simple. Gravity power plant is low cost, low levelized cost, high round trip efficiency. It has minimal environmental impact once it's built. It is very land efficient. We'll address that in a moment. And it's easy to site and easy to obtain permit. This is the technology. Jim, please take this.
Thanks, Steve. The gravity power plant uses entirely commercial off-the-shelf technology, but arranged in a new and unique configuration. It consists of a deep vertical shaft containing a large rock and concrete piston with a steel surface, the piston being half the depth of the shaft to maximize storage. A stationary seal assembly is built halfway down the shaft. A powerhouse containing a pump turbine and motor generator is near the surface. A penstock pipe connects the pump turbine to the lower part of the main shaft, and a tail race pipe connects the pump turbine to the upper part of the main shaft. And finally, an electric power line connects the motor generator to the grid. Now, the shaft and piston are constructed using conventional mining technology. People are very good at excavating big holes. We've been doing it for a very long time. And we put a barrier in the shaft wall to prevent the inflow or outflow of water into the ground. The powerhouse uses conventional hydropower components operating at conventional pressures. To store energy, the pump turbine pumps water out of the upper part of the main shaft using electric power from the grid and forces that water down the penstock into the lower part of the main shaft. Hydraulic pressure then raises the piston, storing gravitational potential energy. To release energy, the piston descends in the main shaft as required, forcing water back up the penstock through the turbine and back into the upper part of the shaft, generating electric power just like any hydropower system. Now, in theory, this system can be constructed at almost any scale. We built one in the lab that's about 7 feet tall. In practice, gravity power plants can be economically advantageous with storage capacities ranging from 200 to more than 2,000 megawatt hours. So these are pretty good sized plants. And power levels from 50 megawatts to more than 500 megawatts. Due to scaling effects, these systems get progressively more cost-effective as they get larger. Bigger is better. So that's the design in a nutshell. Back to you, Steve.
Thanks, Jim. Excuse me again. So in terms of environmental impact, once a gravity power plant is built, the environmental impacts are negligible. There's no impact on wildlife. There's no water use after the initial charging. There's no impact on water quality. As Jim mentioned, it's field, so there's no inflow, outflow, so it doesn't affect surface water or groundwater. No impact on air quality. It's quiet. It's visually unobtrusive. Gravity power plants are also flexible in terms of where they can go. We can put a gravity power plant basically anywhere that the underground rock conditions are suitable. So we can co-locate it with a wind plant or a solar plant or a nuclear plant. We can put it on the site of a former coal-fired power plant or even a former coal mine where we can take advantage of the hole that's already dug in many cases. We could also put it, if it makes sense from a transmission point of view, we can put a gravity power plant in the middle of a city. because it doesn't have a very large footprint. So if it makes sense, we can put it in Brooklyn or Long Beach or wherever our customer wants it. Gravity power plant is also extremely efficient in how it uses land. And as one illustration of this, this is a typical pumped storage project. It's located in California. It stores about enough energy for 1 million homes. So, it would be like if you built 12 of these, it would take care of the problem that I was describing before on the duck curve. It occupies about 12,000 acres. Here is the footprint of a gravity power plant, which stores the same amount of energy, and it's only about 30 acres. So extremely land efficient, which is a major part of our environmental pitch. We're also a good fit for a decarbonizing economy because our technology leverages the human and technical infrastructure of the fossil fuel industry. Basically, Jim was just describing what a gravity power plant is. Basically, to build it, you dig a deep hole in the ground and you build something in it. And coal miners have been doing that for decades. So coal miners know how to do that. We anticipate being able to create a lot of high-paying blue-collar jobs as we deploy our fleet. So this is another aspect to why gravity power is appealing in our current situation as a country, as a planet, really. But of course, electricity is a commodity business, and in commodity business, it's all about levelized cost. Think about the electric utilities. They have customers that are buying electricity from them. They want to keep their costs per kilowatt hour low. That's their levelized cost low, so that they can serve their customers' needs and stay in good graces with the regulators. And gravity power has the lowest levelized cost of any of the technologies out there. And you can see that in this chart. I should mention this model was developed by the Pacific Northwest National Laboratory. That's one of the national energy laboratories, which is part of the U.S. Department of Energy. And they developed this model as a comprehensive view of costs. So they take into account everything: construction cost, all capital costs, O&M costs, end-of-life costs, round-trip efficiency, cost of money, everything. They wanted to get a comprehensive view of everything which goes into the cost, so that utilities and regulators could make informed decisions about these technologies. And you can see why we have this big cost advantage in these charts. This chart on the left here compares the levelized cost of a gravity power plant to a lithium plant, and you can see that our big advantage is in levelized CapEx. And when I say CapEx, forgive me for using jargon, I mean capital expense. It's basically construction cost, engineering cost, all of the first-time costs which go into creating a gravity power plant or any capital asset. And the reason that we have this capital cost advantage is shown in the chart on the right. Jim was alluding to this earlier, but this is really an extraordinary thing. And this is kind of where our, what they call secret sauce. This is where our secret sauce lies, is that every other storage technology that we're aware of scales arithmetically, which is to say, if you make it twice as big, it costs twice as much, and it stores twice as much. With gravity power, if you make it twice as deep, it costs twice as much, and it stores 4 times as much energy. So if you make it big, you get some really attractive economics. And big is what is needed. In order to decarbonize the grid, we need to build a lot of really big storage plants. This technology is something where we can really get some very favorable economics when we get up into the sizes that we're talking about. For us, we want to be building plants that are 1,000, 2,000, 3,000 megawatts and up, megawatt hours and up. So that would compare to the pump storage product that I showed you before, which is about 12,000 megawatt hours. So we would build 4 of our plants occupying about 30 acres to cover that same need on the grid.
1,200 megawatt hours.
I beg your pardon, Jim?
1,200 megawatt hours.
What did I say, kilowatt hours?
12, you said 12,000.
But the Castaic plant is 12,000
1,200.
megawatts. 1,200 times 10 hours.
You're right.
Sounds like we're going to have a debate afterwards. So thanks, everybody.
Yeah.
Anyway, here you're going to see the impact of the economics on the economics of a gravity power plant on the grid. So if you look at a grid, this chart compares the levelized cost of a gravity power plant on the left, a lithium plant in the middle, and a natural gas peaker plant on the right. So off-peak energy is cheap. It's a few cents per kilowatt hour in almost all markets. Peak energy is expensive. In the United States, the average cost of peak energy is 15 to 20 cents per kilowatt hour. That's driven by natural gas, as you can sort of intuit from looking at this chart. So what gravity power plant is, it takes that cheap energy and turns it into expensive energy, creating a value uplift of somewhere in the vicinity of 10 cents per kilowatt hour. Our revenue is a licensing fee, which amounts to 1 cent per kilowatt hour, which we put in the CapEx. So from our customer's point of view, gravity power looks like a screamingly cheap bargain. But from our point of view, that 1 cent per kilowatt hour is quite lucrative. It drives a very good business model where we're making millions of dollars in profit on each plant. I also want to mention that we believe that today is a very favorable time to be introducing that technology to the market because the environment for project financing is quite favorable. And there's a couple of reasons for this, and both of these came out of the Inflation Reduction Act, which the administration or which Congress passed, I think it was last year. The first is that if anybody who builds an investment, anybody who builds a storage plant can get an investment tax credit of somewhere between 40 and 60% of basis. A basis is basically your capital costs, construction, engineering, permitting, interconnection, et cetera. Excuse me. And that's basically free money. So what that says is that Uncle Sam is going to pay for half of your plant right off the top. And then the second thing, which is really interesting from our perspective, and that is the Loan Program Office at the U.S. Department of Energy has the authority to guarantee $400 billion in loans for innovative projects like this. And they are specifically tasked with financing pre-commercial technologies which, like ours, are not quite mature enough for the banks to finance. This office has a lot of money out there that they are using to push these kind of promising, innovative pre-commercial technologies into the marketplace and get them commercialized by seeding these first few projects. So the loan Program Office has, as I mentioned, about $400 billion in authority to guarantee loans, and they've only placed about $100 billion of it. So they've got $300 billion in dry powder. And they have told us that they are looking for projects like ours of $1 billion or up that they want to mandate, that they want to finance. Okay, so Brad.
Yes. Slides here. Let me tell you more about our team. You have met Steve. Our other independent director is Bob Weissenmiller, former chairman of the California Energy Commission, a global thought leader in the area of keeping the grid stable while we shift to renewables. Tom Mason is our VP for Engineering and Construction. Tom was formerly president of the Calpine Power Company, where he ran the world's largest global fleet of gas-fired power plants. He holds an electrical engineering degree from Purdue and an MBA from the University of Chicago. We have a strong board of advisors, including world-class experts in our area of activity. These include Dr. Torbjorn Nielsen, an expert in hydropower systems, Dr. Juan Perez, an expert in hydroelectric system analysis, and Dr. Anjan Bose, an expert in power grid control. And back to you, Steve.
So let me just briefly talk about some of the alliances that we've made with major players in the industry, because this is a large part of our strategy for moving the technology into the market. The Robbins Company pioneered the tunnel boring machine, and there's an obvious nexus between their strategic interests and ours. We have an agreement with the Robbins Company to execute a joint R&D project to figure out how to use Robbins technology to bring down the cost of of constructing a gravity power plant. We have Jim showed you before and talked before about how we construct these things. That was using conventional mining technology. We think that using the Robbins technology, we can be more innovative and bring down the cost to make it even more cost effective. I'd also like to mention that the CEO of Robbins Company, a man named Locke Holm, was one of our earliest and major investors. Babendirty Engineering is a German firm. It's one of the leading firms in the world on underground engineering. Babeng did our all the work on developing our initial construction techniques and developed our original cost model. Excuse me again, it's allergies, it's not COVID. So nothing to worry about. CAS is an Israeli firm it's a world-class firm in terms of doing advanced simulation and modeling of engineering projects. So structural loads, fluid flows, and things like that. CAS is really a world-class player in that regard. Merkel Freudenberg is one of the top firms in the world on sealing applications. Jim talked about the seal and its importance in the gravity in the maintaining the integrity of the gravity power system, and we're looking to Merkel Freudenberg to help us on that. And then the National Renewable Energy Laboratory, also part of the U.S. Department of Energy. They're the country's, in my opinion, the country's leading academic institution on advancing renewables, and we have agreed with them that they'll handle our operations testing on our first few plants. And then finally, I want to mention Stantec. Stantec is one of the top 10 engineering firms in the world. They're a publicly traded firm. They're very conservative. They build power plants for utilities all over the world. Utilities are very conservative for good reason. And so Stantec is one of their favored service providers. So whenever a power plant is being built, Stantec is on the short list to provide engineering. Stantec sees the gravity power plant as being important for their client base. So they want to have the gravity power technology to offer to their clients so that when their clients say, we need storage, can we do pump storage? But, then Stantec has to say, well, it'll take you 10 or 20 years, maybe never get into the thing. Maybe it'll never move forward. Here's an alternative. They see gravity power as having a strategic benefit for them and for their clients. And we see Stantec as having strategic benefit for us because it provides us with a conduit into a very large client base. Before Stantec agreed to take this on, they prepared a technical feasibility study of the gravity power technology. They paid for it, by the way, we didn't pay them. And the study concluded that the gravity power technology is in fact feasible, it is buildable, and it will perform as projected. I think their calculations and Jim's projections were within about 1% of each other. The leader of this relationship at Stantec is Jason Hedin, who's the head of their civil engineering for energy projects and hydroelectric projects in general. Jason was going to be on this webinar so that he could answer any questions that you might have, but as it happens, he's on an airplane as we speak. However, he is available if anybody has any questions about the technology that they want to hear Stantec's take on, other than ours. Jason can be reached through the discussion section on the Gravity Power offering page. I'd also like to mention that Jason has invested his own money in this offering through the Start Engine platform, and we didn't ask him to. We didn't even know he was doing it. He just did it, and that kind of thing. I mean, having Jason, investing in the company, putting his money into it, and having Stantec, deem our technology feasible and wanting to have it offer their client. That kind of validation from a conservative firm like Stantec or an individual like Jason, that gives us a lot of confidence that we really have a winning solution here to move forward with. So thanks, Ashley. That's all I have to say.
All right. Thank you guys, Steve, Jim, and Brad, for that fantastic presentation. As a reminder, if you just hopped in a little bit late, there is a Q&A chat box below. So drop your questions in there if you have any questions around the presentation that we just did. I do see some fantastic questions that have come through so far. So let's get started with those. The first question that we have is, do you have any notable partnerships that you can point to?
I think I just did.
Yeah.
You know, Stantec, Robbins, you know, those are both companies that are you know working with us or slated to work with us on R&D and on commercialization, and who have put their money and resources and time into making us successful. And then the other firms we mentioned. So it's a good question. I think, you know, that is key for a company like ours, you know, to enter into a market like the utility market. It's key that we be allied with major companies with a lot of market heft. In that respect, Ashley, let me say something. There's a post on this in the discussion section, but you know, to break into a market like this, where the companies we're dealing with are major players with big balance sheets, you know, it takes a lot. It takes a lot to get over that hump, to get an emerging technology and overcome first of a kind risk and get it established in the marketplace. It's a challenge that we do not underestimate. And having Stantec and Babin Doherty and Robbins and Roker Freudenberg on our side and getting there, well, that's a big help.
And as Steve had mentioned about the discussions page that is on their Start Engine campaign page, I'm going to drop the link in again in case you guys hopped in late, so you have easy access to that. So that will be in the chat box below for you guys to take a look there. Next question we have is, what are the top 3 reasons why an investor should invest in Gravity Power?
Ooh, well, I guess, oh, you caught me by surprise with that one. Okay, so in summary, you know, if you kind of you want a one sentence, it's a huge market with flawed competition and a very compelling value proposition. So you know, we have a situation. I mean, you know, we have to take carbon out of the electricity supply if we're going to survive as a species. To get there, we have to have storage, and there doesn't seem to be anything else out there which can promise what we can promise: low levelized cost, high efficiency, minimal environmental impact. So we have a path to enable us as a species, or enable the industry to solve the problem of global warming from electricity supply without raising costs for consumers, without damaging the environment, without wasting energy. So that, to me, is a pretty compelling value proposition. If you want kind of more color on that, you know, you can look around. I mean, we've had, you know, quite a bit of success. We got 100+ investors through this offering so far, more coming in every day. Also, if you look around at the industry as a whole, there's investor money just pouring into energy storage sector. There was an article. I think there's a link to the article in the discussion section about all the different venture capitalists and institutional investors who are looking for solutions in energy storage. So there's a huge amount of interest from customers, from investors. So I think, you know, this is a train which is really gaining a lot of momentum, and we would love to have everybody on it along with us.
And given the importance of sustainability and ESG considerations in today's environment landscape, can you elaborate on how Gravity Power's technology aligns with these principles?
Sure. So that's environment, sustainability, and governance, correct?
Environmental, social, and governance.
Okay, so environmental, we've talked about this, and you know, if we're going to save the planet, we have to decarbonize electricity. We have to have storage to do it. We are, as far as we can tell, the only technology that can do that without raising costs and without damaging the environment. But in terms of social, I think we also touched on that back when we were talking about how we build these things. I mean, like you know, if you want to use lithium for storage, well, you know, the lithium is going to come from Bolivia, and the batteries are going to be made in China, and they're going to be plopped down in the United States, and it's going to be all, you know, not all, but it's going to be predominantly money which goes out of the country. If you're going to build a gravity power plant, most of the cost is local content. Jim, correct me. What's our local content and labor percentage?
Um, construction is a very large part of the system, so something on the order of 60% of the cost of the system goes into the local economy.
And those are blue collar jobs, Ashley. You know, those are coal workers and oil workers and, you know, people that you know, are being left behind by what's happening in the economy these days. So this is really good news for, you know, coal country in West Virginia and Wyoming and Ohio and Appalachia in general. And also, I should say, you know, all our cost models are based on labor rates of like $100 an hour, all in labor rates. That includes margin and everything. But what that tells me is that we're going to be paying people really well and still having a very viable cost structure for our customers.
And how do you plan to address potential regulatory challenges and policy changes that may affect the energy storage market and your business?
Jim, do you want to take that?
It's kind of an ambiguous question. How do you address a challenge that hasn't happened yet? In general, we have fewer problems with challenges of various types than most of our competitors. I mean, pumped hydro is the case in point. In spite of all the difficulty of building pumped hydro plants, they still have captured more than 90% of the stationary energy storage market. I think our technology eases the constraints of regulatory requirements rather than make them more difficult. But we also have no toxic chemicals. Our system is built out of rock, concrete, and steel. I'm not sure what else I can say about that.
That works. That's a good answer.
Let me, I can add one thing. I think Jim's point is well taken, is that we are environmentally benign for projects once they're built, and that greatly eases the regulatory process because it's the environmental processing which is the major obstacle for energy projects. Having said that, though, I should, you know, I mean, I want to readily acknowledge that we have to go through the same permitting process as everybody else. We got to meet all the relevant codes, and we've got a list of 30 or so relevant codes that we have to meet for each project, as every other project has to meet. I would also add to it that regulations are cut and dried, and they're generally implemented by professionals, but it never hurts to have political support. And I think the fact that we're creating so many jobs for people that need them is going to be helpful to us in terms of building that kind of favorable environment where people look kindly on what we're trying to do.
And how would you say this helps the average family?
It helps the average family because it mitigates global warming, which means, you know, all kinds of things for the average working family, while not raising their costs. You know, this is an opportunity to decarbonize the grid while not raising and, in fact, probably reducing the cost of electricity. You know, when we talk about global warming, it's a phenomenon which tends to get more attention from knowledge workers and from the elites. I hate that word, but you know, from people like the folks on this webinar. And I'm talking about all of you people, but global warming and that kind of thing, the impact is really felt most severely by working families. You know, they're the ones that are losing jobs in coal mines. They're the ones that are suffering in floods and in droughts. They're losing their crops. So I think that you know, this is global warming is a real existential threat to humanity and something which we all share.
I'd like to add a little bit to that too, Steve, and that is that I think a lot of people have the idea that dealing with global warming is going to be very expensive. But it turns out, particularly in the electric power industry, making these changes, adding a lot of storage and switching the grid to renewable energy saves a huge amount of cost. It's far less expensive than just continuing business as usual with fossil fuels. So that's going to directly impact families in the pocketbook.
And then, given the enormous potential of the energy storage market, can you outline your go-to market strategy and timeline for commercialization?
The short answer is no, but I'll try. Our path forward is the next thing we want to do, and this offering, this RAISE campaign is part of it, is to build a demonstration plant. And that could be done. One possible way to do that is to build a gravity power plant in an existing missile silo. There are hundreds, 200 or 300 abandoned missile silos around the United States that are available cheap. So we could build a gravity power demonstration plant in one of those, or we could just dig a hole ourselves from scratch. It appears in the, based on the experience of the last few years in the storage industry, that having a working prototype like that, not the lab bench test that Jim was describing before, but something in the ground connected to the grid, is all important in terms of getting commercial traction. An example of that is a company called Energy Vault. Energy Vault has their own problems, but they have been very successful in raising money and in advancing into the commercial marketplace. They built a single prototype in Switzerland, small thing, didn't amount to much, but it was enough for them to go public. They went public maybe a year and a half ago, something like that, at a market cap of $1 billion, all on the strength of that one prototype. Now, as I mentioned, they have their own problems. Their market cap is now down to about 400 and some million. And that's another whole subject as to what happened with Energy Vault. There is a discussion on that, by the way, in the starting in the discussion section of the Start Engine offering page. There's a one of the topics addresses Energy Vault. But in any case, that appears to be a critical step for us, is building that demonstration plant. And then once the demonstration plant is built, then we think we have a path forward to use the Loan Program Office and the investment tax credit to get the first few commercial scale projects built and underway. And then once we've built one or two or a handful of commercial projects, then we think it's going to be easy to go forward. There's a saying, I mentioned before that the electric utility industry is very conservative, and for good reason, because they take care of a vital commodity that underpins our entire economy. And so they tend to be very interested in innovative solutions which can make their job easier, make their system more cost efficient and effective, but they tend to be allergic to first of a kind risk. There's a saying in the electric industry that everybody wants to be first to be second. And so we just need to kind of get that first project or their first project or two built using the techniques that I was just describing, and then we think it's going to be pretty straightforward writing orders. Oh, I'm sorry, you asked about the timeline. I also don't want to gloss over that subject, because this, I mean, all of us, all the three of us here on the seminar, on the webinar today, have a substantial investment in gravity power, and I regard this, and we all regard this, as a long-term investment. This is not something we're going to be able to exit in 18 months. I doubt it very much, at least. To our way of thinking, the risk-reward ratio more than justifies that. But these things take a while to build, and so it's going to be a matter of a few years before we really are in a position to start to show a profit.
And is there a target or ideal location to install?
Jim?
Some of the most attractive locations are what Steve referred to before as brownfield sites. There are a lot of defunct coal-fired power plants in the country and around the world that already have infrastructure in place. They have connections to transmission lines, they have switch yards, they have a fair amount of land. And because they're already disturbed, permitting on those sites is much easier than in a greenfield site that hasn't been disturbed. And on top of that, a lot of them are in areas where there are people who need the kind of jobs that Steve has alluded to. So those are kind of some of the most ideal sites, and those sites exist all over the world. But beyond that, it depends very much on the requirements of the local grid. In some places, it will make sense to put large storage plants near very large renewable energy installations, solar power plants or wind farms. In other places, it might make more sense to put the storage closer to the load, closer to a city. And part of it depends on the availability of transmission lines. There are a lot of things that people disagree about in the electric power industry, but one thing almost everybody agrees on is they all hate transmission lines. They're very hard to get built. Nobody wants them on their property, but we have to have them to make the system work. And by placing storage strategically, you can minimize the requirement for new transmission lines and make the existing transmission lines work to a larger percentage of their capacity. Because of our small footprint that Steve described, we have the flexibility to put plants in many places, including near load centers.
And what are the main risks and challenges that Gravity Power faces, and how do you plan to mitigate them? Are there any regulatory or environmental factors that could impact your operations or growth?
From my perspective, the biggest risk is financial. We're talking about big plants. If you look at the electric power industry, the system is dominated by big plants, both in the fossil fuel industry, in the nuclear power industry, and in the renewable energy industry. Many solar power facilities now are in the gigawatt or range or above. Nuclear power plants are routinely a gigawatt or several gigawatts, several nuclear power plants. All of these plants that size cost an awful lot of money, which contributes to the conservatism of the utility industry that Steve described. We need to get to that scale. Once we have plants of significant scale working, then we can scale up to optimally sized plants, which are up in the 2,000-3,000 megawatt hour range. Plants larger than that probably aren't as attractive. They are actually a little bit more cost effective, but they take longer to construct and it requires raising more money. So it's probably better to build 2 or 3 relatively small plants, meaning 2,000 megawatt hour or so, rather than one huge plant of 6,000 or 8,000 megawatt hours.
Let me elaborate on that a little bit, Ashley. Jim's right. I mean, a gravity power plant is expensive. It's like, hundreds of millions of dollars per plant. Now, in the electric business, that's touch money. I mean, utilities spend billions and tens of billions of dollars on energy projects all the time. So there's nothing inherently problematic about the cost of a gravity power plant. The question is the risk associated with the first few. And our strategy for overcoming that risk is probably the biggest hurdle we have. And again, there's a discussion about this on the offering page. I encourage everybody to look at that for a little bit more detail. Getting that first project built, or the first couple of projects, that's going to be the biggest hurdle that we face. And our strategy for that is the two things that I mentioned before, the investment tax credit that takes out half the risk right away, and the loan program office, the guaranteed loan program office, which takes out the other half. So, you can almost get the project for free if you're the utility adopting it. And then there's a third element of that strategy, which I'd like to mention, and that's assembling a consortium of users. And sometimes it will happen that utilities will be interested in a technology, and in order to mitigate the risk of the first project, they'll form a consortium. And so that way a group of utilities will share the risk and they'll all benefit from implementing the technology. An example of that is a nuclear power plant in Utah, which is a modular nuclear plant. That's different. The big nukes you have, they're built from scratch. The modular nuclear plants, they're basically tubes that go in the ground, and they're self-contained nuclear plants, and they're not quite a commercialized technology. So a group of 6 or 7 utilities, mostly located in Idaho, I believe, got together, formed a consortium, and now they're proceeding with this project in Utah. So the combination of those techniques, we think, is what we're going to be using to overcome that first of a kind market friction and get the technology commercialized.
And there's a funny factor here that I want to mention just quickly, and that it's a question that a lot of people don't seem to be asking, and that is, assuming you have a technology that looks attractive, and you build it and it's technically successful, will it solve your problem? If you look at a lot of the energy storage technologies people are proposing, the answer is no. Even if they're technically successful, even if they start building them out, they can't be built at large enough scale or fast enough to solve the problem that we have with the electric power grid. So that seems to me to be a fundamental requirement of a technology. It's a risk that people don't frequently think about. Are you going to solve? Is this going to solve your problem? What is the risk of not solving your problem by spending money on a particular technology?
And what specific roles do your key industry relationships with the ones that you had mentioned on the previous slide play in advancing your technology towards commercialization? And how have these partnerships been leveraged so far?
I can take that one.
Sure.
Freudenberg has worked with us since several years back. They designed our seal elements for the seal system. So having a company that is highly experienced in seal technology is kind of critical to making the system work. The first commercial systems we build don't require any new technology. Everything we need to build those systems exists today. We worked with Babeng out of Germany to develop a construction plan and cost model to figure out if it would actually be cost effective to build these systems. How do you build a shaft as big as we need? There are mine shafts several times deeper than any shaft we will need that have been in existence for decades. So it's the technology for building those shafts is clear. But after we get the first commercial systems built, where do we go from there? Nobody has built shafts as big as we want in the quantities that we want. So there's lots of opportunity for new technology to make it faster and cheaper to build big shafts, excavate large shafts, and build the systems that go inside those shafts. So having people like Robbins and Stantec involved is going to be critical to developing those new technologies and trying them out and driving down the cost. We need to get on the bandwagon. I mean, any technology that's produced in large volumes gets cheaper and better the more of it you produce. And that will be true of our systems as well. The more we build, the better they'll get, the cheaper they'll get.
And it's impressive that Gravity Power's technology is considered the most cost-effective among 14 storage technologies. What specific features or characteristics of your technology allow it to outperform other storage solutions, and how do you plan to maintain this competitive advantage as the market evolves?
Well, the second part of that I just alluded to,
Yes.
right? Once we start building systems, there are we've already thought of some new kinds of excavation equipment that could be built that would make our systems faster to build and cheaper to build. Let's see.
Let me offer one thought on that, Jim, if I may.
Okay.
I'm located in Silicon Valley, and in Silicon Valley we have a saying that only the paranoid survive. I think the short answer to the question is that we're looking over our shoulder all the time. There's a lot of smart people out there working on this, and we have a robust patent protection around what we think is an extremely powerful technology. But we also are fully aware of the fact that, along the lines of what Jim was saying, we got to be moving forward as fast as we can, improving this as fast as we can if we're going to stay ahead of the competition.
We do have some fundamental physical advantages over a lot of competitors. I mean, and we've talked about them. The largest material contribution to our system is rock that's in the ground where we build the system. So we get that for free. We need some steel, and we need some cement to go along with that. Also, the scaling factors. The energy content of the system is MGH, right? Mass times gravity times the height the mass is lifted. And so, as Steve talked about, if you make the system twice as deep, you get 4 times as much energy, but it costs less than twice as much. That's a really powerful advantage. There are also scale factors in terms of diameter. If you double the diameter, it quadruples the mass, but the cost of the containment wall only doubles. So there are factors like that that on top of that, surprisingly, it was surprising to me anyway, when we first started working on this, we found that hydropower equipment is dramatically cheaper as it gets bigger in terms of cost per megawatt. A 400 megawatt hydro turbine is something like a factor of 5 cheaper per megawatt than a 40 megawatt hydro turbine. So we have all of these fundamental scaling factors that are heavily in our favor that most people just don't have.
Okay, great. So we only have about a minute left in the webinar for today. So with the Gravity Power team, is there anything you want to leave the audience with before we conclude?
First of all, thanks so much for joining us. I've really enjoyed this process with Start Engine. We've just got so many great questions coming in today and coming in through the discussion section. So it's really been a pleasure to have this back and forth with investors. I think, the overall picture here is one where this company and this technology has tremendous promise. I mean, this is a very high reward investment, high potential reward investment. But it also is, we've got lots of challenges ahead of us, and we don't underestimate that. So, we regard this as being an opportunity to make a big difference, make a big dent in global warming, and potentially have a very, very profitable investment. But it's at the cost of, undertaking a lot of challenges at this point. And so, what we're looking for is customers that kind of share that vision of the importance of mitigating global warming and the importance of doing so without raising costs and without damaging the environment, and who have the kind of long-term perspective on their investments that we have. So I guess that's where I would leave it. Ashley, Brad, anything you want to add, or Jim?
No, I think you've covered it pretty well, Steve. Um,
Professor, what about you?
Well, I'm a big believer. I think you saw that we have a wonderful team. We're going to be able to execute when we get the funds in to do this, and it's a very exciting sort of world-changing technology and adventure. So I appreciate everybody's support.
Fantastic. Well, thank you guys so much for the fantastic presentation, taking your time to answer all of these questions. And thank you so much to the audience for asking all of these fantastic questions and joining us and taking time out of your day to view the Gravity Power webinar. So please visit the Start Engine campaign page as well. If you have any questions after the webinar is concluded, you can ask those in the discussion section. But thank you again to everybody, and I hope you guys all have a great rest of your day.
Thank you, Ashley.
Bye.